Welcome to Chapter 7. We would like to now take a look at the first section in Chapter 7, 7.1. And this is a very significant step for us in Chapter 7. We're going to begin to actually use statistics and our statistical tools to make meaningful inferences about populations. And the kinds of results we're going to learn how to produce in Chapter 7 are the kinds of results you see reported in magazine and newspaper articles or on websites or even on news broadcasts regularly. So we are now going to get to, for the first time, use our statistics to provide results that are the kind of results you see in professional demonstrations of statistics. Now, it's a big topic, as we can see here from the count down here. There are 54 slides in this slideshow introducing the first section of Chapter 7. So we will not be able to get to go through all of that today. However, I want to give as much of a meaningful introduction as I can, and then keep in mind you can always see the complete set of slides by pulling them up in the multimedia library feature of our MyStatLab website. You can always go back and pull these slides up for yourself to use in whatever way you see fit. All right, so having said that, let's get going because there's lots to do. So Chapter 7 is about estimating parameters and determining sample sizes. So again, remember, the parameter is the value for data from the entire population, as opposed to a statistic, which is just a data value resulting from a sample from the population. And from day one, the purpose that I described for statistics is that you collect a sample from a population to then try to infer things about the overall population of everybody. So to be able to take a sample and look at the sample and then estimate a parameter's value, like the average height of all students at DVC, or the portion of students at DVC that would call themselves Democrats or something like that, to be able to take a sample and then make that estimation is what we're going to do rigorously for the first time now in the beginning of Chapter 7. So let's look at our sections. So as you'll see from our homework assignments, we only are covering the first 3 sections of Chapter 7. 7.4, the bootstrapping section, is an optional section which we will not be covering. And so what do they do in these 3 sections? They basically look at estimating 3 different things. 7.1, estimating a population proportion, like I was introducing before, the idea of a proportion of the population. For example, the proportion of DVC students who would label themselves as Democrats. A proportion is a percentage. It's like 40% of the population, 70% of the population, which fits into a certain category. Then in 7.2, we'll look at estimating a population mean, like the mean height of students at DVC. And in 7.3, we'll look at estimating a population's standard deviation or variance. So in all 3 cases, we are talking about how to make an actual estimation of some parameter for the population. And so most of the ideas about that are introduced in 7.1. So 7.1 is somewhat longer than the other sections, because then in 7.2 and 7.3, we will do those same things we introduced in 7.1, but for those other parameters. So 7.1 has a lot for us to discuss. Let's go on to the key concept. So this section presents methods for using a sample proportion to make an inference about the value of the corresponding population proportion. Here are the 3 main concepts included in this section. First one, point estimate. The sample proportion, p hat, is the best point estimate of the population proportion. So if I wanted to just give a value to approximate or estimate the proportion of students at DVC that call themselves Democrats, the best way to do that would be to take as large a sample as I possibly feasibly could, and then look at the proportion of my sample that labeled themselves as Democrats and make that sample proportion the estimate for what the overall proportion would be. However, as you can imagine, how likely that sample proportion is a good match with the population proportion would depend on how big a sample that I have. And so to just take a sample and use its value to estimate the population is a starting point. It's the best point estimate where you just give a value you think it's your best guess. And definitely the larger the sample size, the more likely that sample guess will be close to the actual value. But nonetheless, there's a weakness to it in the sense that there's no rigorous statement about how good your data point estimate would be. Like, what's the likelihood that it's fairly close or not? So a much more sophisticated type of inference about the population is called a confidence interval. So a confidence interval, part 2 here, is where we can use a sample proportion to construct a confidence interval estimate of the true value of a population proportion. So what does that mean? Here's an example of a confidence interval so you can wrap your mind around it as soon as possible. So let's say I take my sample of 100 students from the DVC student population, and I ask them all, how many of you would consider yourself a Democrat? And let's say 30% say they consider themselves a Democrat. So I could just stop right there and say, okay, my best point estimate is that 30% of all students at DVC consider themselves a Democrat. All right, well, how much do I expect that to be close to the real value? Does that mean that maybe the real value is 50% and I just got 30% and I was 20 percentage points off? Or would I think that that's unlikely? It's a very weak statement to just give my point estimate. So instead, I could use the point estimate, I could use the value I got from my sample along with the sample size, and I could do some math behind the backgrounds. Thank you, StatCrunch, for doing that for us. And I could instead make a statement something like, based on the results of my sample, I'm 95% sure that the range of values between 28% and 32% contain the actual portion of students at DVC that call themselves Democrats. So I would be giving an interval of values that the actual population proportion calling themselves Democrats is between 28% and 32%, and that I'm 95% sure of that. That's an example of a confidence interval. And we'll define it very clearly. We'll show you what it means, how it's calculated, things like that. But the idea is that a confidence interval is where you don't give a value that you think is your best guess, but that you give a range of values and you believe that that range of values has a certain percent of likelihood. There's our probability concepts coming into play. A certain percent likelihood, I'm 90% sure, 95% sure, I'm 99% sure that this range of values contains the actual proportion of the population that calls themselves Democrats. And you can determine what level of a surety you want to use. If you want to be 99% sure, you can do that by either adjusting your range or by making sure you have enough people in your sample size to get that level of a surety. So it's more complicated, but what it's saying is more powerful and more concise. And then finally, of course, if you are starting to make a confidence interval and you want to be able to control whether you're just 90% sure about the range or whether you're 99% sure, and how tight the range is based on how many people you sampled, then the third thing is you would like to know, how would you find the sample size necessary to estimate a population proportion with the level of accuracy that you want? And obviously, to get greater accuracy, you probably need to either have a wider range or a lot more people questioned. But you can find out exactly what sample size you would need to get the range to the size you want with the assurity level of how confident or what likelihood there is that that's the correct range. So that's a lot. And that's why there's 54 slides covering this one section. So I'm definitely going to skip over any emphasis in the slides about formulas so that we can focus more on the ideas and allow StatCrunch to perform the formulas for us. However, we do want to think about what the formulas are doing a little bit so that the ideas can become clear and that we can properly interpret the results of StatCrunch. So I'll just pause here for a second. Are there any questions or comments about any of this that I've just introduced before we move forward in the slides?
So this section specifically builds up most of the things that we're going to also be using in 7.2 and 7.3.
Yes. So for example, we're introducing the idea of a confidence interval, and I've been discussing a confidence interval for the proportion of a population. Like I think the proportion of students who call themselves Democrats is between 28 and 32%. Well, in 7.2, they'll be doing the exact same thing, but instead you'll be giving an interval of values that would contain the mean of the population. So my confidence interval for the mean height of students at DVC might be something like where I say, all right, I'm 95% sure that the range of height values between 5'6" and 5'9" contains the mean height of all students at DVC. So the concept is the same. The idea of what a confidence interval is the same. You'll also want to be able to get the required sample size to hit certain targets for a confidence interval for a population mean instead of a population proportion or for a standard deviation. So these core concepts about point estimate, confidence interval, and sample size will be also then carried out in the next two sections. So learning about them well in this first section is crucial. Does that make sense?
Yeah, thanks.
Other questions? All right, shout them out if you think of something. All right, so the first thing that they introduced, this idea of a point estimate. The point estimate is a single value used to estimate a population parameter, like 46%. The sample proportion, remember the little hat on above means that's the proportion of your sample, is the best point estimate of the population proportion P. Now keep in mind, the larger your sample, the better that estimate will probably be. But in general, once you have a sample, if you're curious about the population proportion P, the best estimate you could make for that would be to just look at the proportion from your sample. So this is because this is what we call an unbiased estimator, which we discussed a little bit in chapter 6. We use P hat as the point estimate of P because it is an unbiased and it is the most consistent of the estimators that could be used. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distributions of all different samples of the same size, the statistics you would get from every one of those, the mean of all of those sampled values is actually equal to the corresponding population parameter. So if I looked at every 100 ways I could take 100 students to DVC and every one of them, I look at their proportions of Democrats. If I averaged all of those sample proportions, I would get the population proportion. And for that reason, P hat targets the population proportion. So a little bit of chapter 6 logic in there. But in general, you want to walk away with the idea of what this is saying, that that the P hat is an unbiased estimator for the population proportion and that it targets it, meaning when you take different samples, they're trying to fall around the real value. So that's a good estimation. So let's look at an example. A Gallup poll was taken in which 1,487 adults were surveyed and 43% of them said they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. So what do you guys think?
So for the point estimate, then, would we take the 43% and use that as it?
That's exactly right. And so it's good to just pause here and go through all of those words and the paragraphs that were just giving us. And it basically boils down to look at the result of your sample and take the result of your sample and use that as your prediction for the population. So because this was a sample, then this is p hat. And as we were just discussing, p hat is the best predictor, it's the best point estimate, meaning single value estimate as opposed to a range to estimate. So that would imply that 43% is best guess at p, meaning the proportion of the actual population that that have Facebook pages. All right, so that's our starting, not too deep, but the ideas are going to start to grow quickly. So we want to feel comfortable along the way. Because the sample proportion is the best point estimate, and the sample proportion was 43%, then our estimation would be 43% for the population. Okay. Now we get to the meat. Confidence interval. This is crucial. A confidence interval, or interval estimate, instead of a point estimate, is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI, confidence interval, as opposed to confidential informant, if you watch cop shows. So the confidence level is the probability that the confidence interval actually does contain the population parameter. So when we are giving a confidence interval, we just don't give the interval by itself. We also give the confidence level of our confidence interval. So example, if I was talking about the proportion of students at DVC who label themselves as a Democrat, I could have a confidence interval of guessing that the actual p-value is somewhere between, I'll just make numbers up, 35% and 45%. So that's the confidence interval part. So then the confidence level would be the probability that the actual p-value is in that range, that that range actually contains the real p-value for the population. Because we're not going to ever be 100% sure unless you talk to everybody. So as we talked about with probabilities, we are going to make probability statements when doing statistics correctly. So I give this range of values, but then I would want to also say something like, I am 95% sure the range includes P, the actual population value, because we came up with that range based on the results of a sample that we took, based on the results of statistics. And as we know, samples can vary. So P, I think, is in that range based on my sample. And with some fancy math in the background, I can say that if I looked at all the different ways that I took samples of this size, and every time I did that, I came up with a different range of values for my confidence interval, 95% of the time, the confidence interval provided by my sample would contain the actual value of the proportion of the population. And so for that reason, I'm 95% sure that the range I have from my sample includes the proportion of the population. So there's two things to a confidence interval. There's the interval itself, and then paired with that interval, based on the sample and sample size, will be the confidence level. Now they're introducing some notation. They're saying the confidence level as the probability that I was describing, they're labeling it with 1 minus A, or 1 minus alpha, I should say. And so we are going to be 95% confident, have a confidence level of 95% when the alpha level is 5%. So you can think of the alpha level as the probability that your prediction is wrong. So if I'm 95% sure that my range contains P, well, that means there's a 5% chance that my range does not contain the actual proportion value of the population. So you can imagine alpha is like the probability that your estimate, in this case an interval estimate, is wrong. And so the lower alpha is, the stronger your prediction is. If alpha drops to 1%, then there's only a 1% chance that my interval value estimate is wrong. If alpha goes up to 20%, well then, by the way I got my interval from my sample, 20% of the time I'd be wrong. And my interval range would not contain the actual population value. And so the alpha, ideally, if the alpha is small, you have a stronger estimation, a more accurate, more likely estimation. And as your alpha level gets big, your confidence level goes down and makes for a weaker estimate. Okay. So they're sort of showing this relationship between confidence level and alpha. And so since it's just the confidence level is 1 minus alpha, then you can see when the 90% is the confidence level, then alpha is 10%. When confidence level is 95%, alpha drops to 5. When confidence level is 99%, alpha drops to 1. And in particular, they're pointing out these are the most common confidence levels that people refer to. So they will produce confidence intervals about which they're 90% confident, 95% confident, 99% confident. Typically, you don't want to go below 90% because then it just doesn't sound like you're really confident in what you produced. Why is it that you wouldn't just go 99% all the time? Because maybe to do that, you either need to have a range that's so large, you're very sure the real value is in there because it's not very specific. I'm 99% sure that the proportion of students at DVC that call themselves Democrats is somewhere between 10% and 90%. Well, yeah, that's because this doesn't cover, it's not very specific. It's such a wide range, it's hard to see how it would not be in that range. So how can I make my range small, but also have my confidence level be high? Well, that's when I would need to make a larger sample size. And so sometimes I don't want to go up to a 99% confidence level because either my range would become so wide in my predictive range that it's not very helpful, or I would need to keep the range small to be 99% confident. I would have to have such a huge sample size. I just can't afford the time or money to do that. So first thing to recognize here is that there are different confidence levels, and that then the corresponding alpha changes since they add up to 1. All right, so let's look at the idea of interpreting a confidence interval. So as I was just describing, confidence intervals are paired with confidence levels, and they're describing what conclusion you can make from your sample about the population. And so because this is a statement that we want to be very accurate in terms of what you're claiming, because there's some complexity here, and we don't want people to misunderstand the concepts and make statistical claims that are not valid or not correct. And so they're going to give us 3 slides here that show you, once on this first slide, the correct way to interpret a given confidence interval, and then 2 wrong ways. And I'm going to just tell you, this is really good to think about and examine, because probably between the first and the second one initially, you're not going to be able to tell the difference, but one's correct and one's wrong. And that'll be this true on the homeworks as well. So let's talk this through and let's look at this together. We must be careful to interpret confidence intervals correctly. There's a correct interpretation and many different and creative incorrect interpretations of a confidence interval. So they're giving us a confidence interval for P, and even though they have it in their statement, they didn't write it here. So let me add on here that the confidence level is 95%. And now we have an interval that is given for P, so that P is between 0.405 and 0.455. And again, these are portions of the population that have some characteristic about them, like call themselves Democrats or whatever. So if you were given a confidence interval saying that I have a confidence level of 95%, and that my confidence interval is that P is between 0.405 and 0.455. Then here's the correct interpretation of that confidence interval. We are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion. So the statement that's correct using statistics, probability, and the formulas that we're going to generate to create these is claiming that the interval itself is that likely to happen to contain what the real proportion of the population is. Because for every time we get a different sample, we might get a different interval. And the one we got from this sample is 95% likely to be contain the actual population proportion. So that's what the statement says. All right, so the only way to try to understand some of the details of why it's important to phrase it this way is to look at the wrong examples that they show us on the next slide. So let's do that, and then we'll see if there are questions. So given the same interval and the same confidence level, here's a wrong interpretation of the exact same thing. Again, the confidence level is 95%. So a wrong interpretation. There's a 95% chance that the true value of P will fall between 0.405 and 0.455. So can you see the difference between the correct interpretation and this incorrect interpretation? Correct one says we're 95% confident that the interval actually does contain the true value of the population proportion. And the incorrect statement says there's a 95% chance that the true value of P will fall in that interval.
Does it have something to do with the fact they said 95% chance instead of being 95% confident?
No.
All right.
So yeah, all we can do is try to pick apart the wording that they use, the order of the wording, and that's exactly something to question. But in this case, saying we are 95% confident and there's a 95% chance, we view these as equivalent. Okay. Those are saying the same thing. So there's something else about the statement, but see if you can find another tweak in between the statements that will help us focus on logically what's different between the two. What do you guys think?
Is it the way they use the P in both things? So in this one, they don't say it's a population proportion P. They just say it's the true value of P.
No. So P is the population proportion. And so if they say P, they're referring to the population proportion. That's just by the definition of P. As I said, I think it's going to be hard to even see the difference between the statements, right? All right, so here's what it is. It's literally that in the first one, they said the interval will happen to contain P. Then in the second one, they said P will happen to fall within the interval. So why is that different? Because saying that the interval that we get will contain P is correct because we get a different interval with every sample. The intervals will change every time you change your sample. The interval values will change. And 95% of the time, you'll happen to get an interval which grabs P. The actual population proportion P does not change. It's a fixed thing that you're trying to find out. It doesn't move around and change its value. What changes in value is the range of values you get to predict it. And those will change every time you grab a different sample. And so what we're saying is that 95% of the time, the range that we got this time will be one of the ones that contains P. If I looked at all the different ranges I would get from all different samples, 95% of the different ranges I would get would contain P, and in 5% of them, the whole range would not happen to contain P. So that's why we're 95% sure that the range we got this time contains P, because 95% of the time, the ranges we get will contain P. Whereas in the second statement, it says there's a 95% chance that P will fall within this range. That suggests by the structure of the statement that P may move around and that 5% of the time P will fall outside this range and 5% of the time P will land, and we got to see where P lands. But P is not changing. It's the interval that's moving, not the P value. The P value exists. It's a fact about the population. And if we talk to everybody in the population, we would know exactly what it was. But since we only talk to a sample based on randomly which sample of people we chose, we would get a different range of possible values. And that range will be the one that moves around. And then we want to be sure, we want to express our surety that the particular range we happen to get from our sample this time, how likely is that it actually contains the real P value that we're looking for? So the problem with this statement is that it says P will fall within this range as if P is a variable, and P is not a variable. It's a set value. It doesn't vary from sample to sample. The range varies from sample to sample. Questions, comments, discussions about that? All right, so since they're giving you this thing and saying, here's what's the right way to draw a conclusion, here's a wrong way to draw a conclusion, and they're going to give us one more wrong one, which is a little more obvious. That means you're probably going to have homework problems like this, where they just give you some conclusions and you have to pick the correct one. And so you have to get comfortable enough with this subtlety about what's the correct way to say it that you can get credit on the homework. And more importantly, on a quiz, or even more importantly, midterm 2 or the final exam, in case they show up there. All right, but it'll take time. Let's look at their second incorrect interpretation. See if you feel more comfortable with that. Same exact range, same exact confidence level of 95%. So the conclusion they're stating here is 95% of sample proportions will fall between 0.405 and 0.455.
First, this is referring to the sample proportions, not the population proportion. Exactly. And then it says it will fall between, which was the same problem with the previous one, where it's the range that moves, not the actual value.
Nice. Well, P hat may move So it doesn't exactly have the same problem as before, because you could imagine every time you get a different sample, you get a different p hat. So p hat might swing around. But we're supposed to be interpreting this statement, and this statement doesn't say anything about p hat. It's talking about p, because we don't care about samples varying around. What we want, what we're investigating, what we're trying to draw a conclusion about is the population proportion. And so this statement is making a claim about the population proportion and the likelihood that that range of values contains it. So to make a statement referring to sample proportions when this claim is nothing about sample proportions is just completely wrong. So you nailed it on the very first instinct that you stated there. Questions, comments, discussion about this? So a confidence interval is a claim that helps us estimate the population proportion P, not a sample proportions. All right, lots to cover. Let's see how far we can get. So this is a nice diagram to really illustrate the subtlety between those statements that I was just discussing. So imagine that you make a 95% confidence interval. That's a process that we're using based on an individual sample. And in the long run, the result in a confidence interval limits for the result for a confidence interval is talking about what portion of intervals that we would get based on that sample size that would contain the true p-value. So they're showing confidence intervals from 20 different samples. So the interval is, this range of values from here to here. And they're saying that P is here at 50. And so if I did one sample, I might get that range of values. If I did this sample over here, I would get that range of values. And notice that range of values is much higher. But it does also contain the population proportion. And that what they're showing there is that out of those 20 different samples they took, one of them, the range of values they got from their sample was low enough that it didn't even contain the actual population proportion. But all the other 19 out of the 20 examples did contain the population proportion. And so if you were taking a random sample, you can see that 95% of the time, the range of values you get would contain the population proportion, and 5% of the time, the range of values you got from your sample would not. And that's why in a situation like this, we would 95% of the time get a range of values that did contain the p-value for the population. And that's why we would say our confidence level is 95%. So hopefully that helps to understand this idea about what a confidence interval statement is. Again, a confidence interval will contain an interval of values, and it will contain a confidence level. And the confidence level tells us if I kept taking samples like this in the long run, what percentage of the time would the range I got from my samples contain the p-value for the population? Okay, so now we're going to get to the math a little bit. So we're going to start to introduce some labels, and we need to get into them a little bit so that we can understand what they're referring to when they talk about a critical value and certain z-scores or z sub alpha over 2 scores as they're showing us here. But they will then use a lot of these labels in formulas to tell you how to calculate things by hand, which we won't really need to do. And I certainly want to de-emphasize, but that doesn't mean that we can't ignore all the labels here, because sometimes they will give problems where they just say, all right, what's alpha over 2? And what is the critical value in this case? So you'll need to come up with the critical value in problems and things like that. So imagine your confidence interval on this diagram, and let's say your confidence interval is 95%. So what this is showing you is that in order to have a confidence interval of 95%, we need one of those situations where the interval of values on our scale from small to big, if I did my normal calculator in StatCrunch and I put in those values, I would need to know that within that interval, there's 95% likelihood the value falls within that interval. That's how I have a 95% confidence interval, because the interval of values I give you, 95% of the probability of getting an answer will fall within that range. And if 95% is my confidence interval, that would mean that alpha is equal to 5%. But what that means is that the ways that you can be wrong are split into two areas. You can be wrong by having your interval be too low to capture a true value, and the true value is to the right of your 95% interval. Or you can be wrong because your interval was too high and the true value was below your 95% interval. And what that means is since there's two places and you want a total probability of being wrong, remember alpha is the chance that your interval is wrong as an estimation, that the total ways of being wrong can be split into being above and below. So that means there'll be 2.5% area above your interval, and there'll be 2.5% area below your interval. Again, this is with a 95% as an example. So what they're saying is that when you are imagining constructing this setup under a normal curve where you have a 95% confidence interval, you would need to have scores on the top and the bottom of your interval, z-scores, such that the area to the right of the right z-score of your interval is only half of the alpha value. And the area to the left of your lower confidence interval value would only be the other half of the alpha value. So they're labeling this as alpha divided by 2 because it's half of the alpha value. And they're saying the number z sub alpha over 2 is the critical value, that is a z-score with the property that is at the border that separates the area in the right tail for the standard normal distribution. Lots of statistics vocabulary in there. So let's try to get clear to the ideas. So the critical value will be the values you need to have your 95% interval be in the right place. If I move that over, then I don't have a 95% interval anymore. And so you can calculate that by looking at your alpha value, taking the alpha value, splitting it into 2 between the two sides of your interval to determine where your interval values should fall. So we'll see this in action, but this is the motivation and the ideas behind the actions that we'll do. So they're going to do an example of one of these. Finding the critical value, z alpha over 2, corresponding to a 95% confidence interval. So as I was just using that as an example, that means the critical value would need to be the z value where only 2.5% is to the right or 97.5% is to the left. So if 2.5% is to the right here, that means 97.5% is on the other side of my critical value. So they're going to walk through that process. They're going to say a 95% confidence level correspond to alpha equaling 5%. So alpha over 2 is 2.5%. The figure on the next slide shows that the area in each of the green shaded tails to get that 2.5% to the very top right or bottom left, on the right end, you need a z-score of 1.96. And again, they're often referred to looking up z-scores to get particular area values on a table, but we've just done that with the normal calculator in StatCrunch. So if I go into StatCrunch and I use the normal calculator and I say I want the area to the right to be 2.5%, then StatCrunch will tell me the z-score down there is 1.96. So that z-score of 1.96, they're referring to now as a critical value. So common critical values, the one that they just showed us was at the 95% confidence level. So when you have 5% for alpha and you split that up on the two sides, then the right critical value will be 1.96. And remember, a normal curve is symmetric. So the critical value on the other end, on the low end of the interval, will be negative 1.96. The critical values for confidence intervals will always come in plus or minus pairs because they're always equidistant around the middle. So if you just want to be 90% confident, well, then you can use a lower critical value of 1.645. And if you want to be 99% confident, you have to go up to a critical value all the way up to 2.575. If you're up at 2.575, then 0.5% of area will be to the right of that. And if you go down to negative 2.575, then the other 0.5% of area will be to the left of that. And those two little slivers of area will add up to 1% of being wrong and 99% of your interval being right. All right. So now we're going to define margin of error. This is going to be to help understand how a confidence interval is created and why it is, what it's saying and why it works the way it does. When data from a simple random sample are used to estimate a population proportion P, the difference between the sample proportion, the best point estimator, the value you got from your sample, and the population proportion is an error. So if I am trying to figure out the proportion of students at DVC who label themselves as Democrats, if the real proportion was 35%, and I took a sample of 100 students and I looked at it and the proportion from my sample was 32%, then that would have an error of 3%, because the value I got from my sample is 3 percentage points off from the actual population's percentage. So that's what the error is. The maximum likely amount of that error is the margin of error, denoted by E. The maximum likely amount of that error. Because in general, you're not going to know what the actual population value is. So you're going to have to calculate the amount of error that you're allowing as a maximum. And when you give an interval, so if I say P is less than 35%, but greater than 25%. Well, I'm still correct if P is anywhere in that range. And the idea in the center of that range is 30%. So the way you get this range of values is you start with your P hat and then you add the amount of error from that P hat above and below your P hat value, and that's how you get your interval. So this interval came from taking the P hat equal to 30% and having a max error E equal to 5%. That's how intervals are constructed. This is using this E. The margin of error is the maximum likely amount of that error. So for example, if I tell you that my point estimate from my sample is 30%, and based on my sample size, I believe that by the way I took my sample and the way I got that P hat, that the maximum error I'm going to have with my point estimate is 5%. That my point estimate will be within 5% of the actual P value of the population. Well, if 30% is within 5%, well, that means P might be as high as 35% or as low as 25%. So if I give that range of values from 25% to 35%, then I'm taking the sample value I got and adding the maximum error that I think could occur to get this range of values. And so what that means is that if you think about this confidence interval, that right in the middle of the confidence interval will be p hat, and then this will be p hat plus the allowable error, and this will be p hat minus the allowable error. That's how the confidence interval is produced. And then you can say, based on your confidence level, that I'm 95% sure that the true proportion of students at DVC that label themselves as Democrats is between 25% and 35%. So the margin of error is how far you allow your range for your confidence interval to go above and below your point sample estimate from your sample. That's your margin of error. So one of the ways that intervals are sometimes given is with the margin of error and the point estimate. And this is how you will see it often given in news articles or magazines or on TV or on webcasts or whatever, is they'll say, well, based on our sample, we predict that the proportion of students at DVC who call themselves Democrats is 35%. No, I'm sorry, 30%. I want to use my same numbers here. So our prediction is that it's 30% because that was their p hat. And then they'll say something like plus or minus 5%. Or they'll say literally with a margin of error of 5%. You see this all the time when it's election time and they poll people and say, we said that 42% of the people support Joe Biden, and that's with a margin of error of 3%. So that's a way to give you a specific predictive value so that you have something simple to look at, but then the margin of error actually gives you a range, a confidence interval of values. Really, when they say a number plus or minus 5%, well, you would add that number and subtract that number, the plus or the minus, to get the range of the confidence interval that they're actually using as an estimate. All right, so I did my best. I'm now past time a little bit. Okay, I'm going to try adding some recording after class has ended. I just finished class. We ran out of time just trying to get through the bulk of the concepts in the first part of the slides here. But I didn't have time to go and just show right on top of this what it looks like to use StatCrunch to do a homework problem with a confidence interval. So I would like to add that to the video even though I'm no longer live and the class is over. Okay, so I'm looking at number 10 on the homework set, and this is in 7.1 as we can see. And so the problem states the data given to the right, and there's this big pile of data here, includes data from 34 candies, and 9 of them are red. So we can see here these 9 are red, and they're giving the list of the weights of each of these candies. The company that makes the candy claims that 31% of its candies are red. Use the sample data to construct a 95% confidence interval estimate of the percentage of red candies. What do you conclude about the claim of 31% being red? So right out the gate, what we want to do in this problem is construct a 95% confidence interval estimate for the population of percentage of candies that are red. And then they want those given as percentages here. So the data that's given here is really showing the weights of the candies, which has nothing to do with the proportion of the candies that are red. So that might be misleading. I don't want to put this data in StatCrunch. It's not helpful. So let me illustrate what we want to do here. I'm going to open up StatCrunch. So we're going to be using some new tools in StatCrunch when doing confidence intervals. I'm going to go to the Stat tab, and I'm going to show you now a group of 4 of my choices here that we're possibly going to look at using in Chapter 7. And you'll see other examples to illustrate their use. They are, as a group, z-stats, t-stats, proportion stats, and variance stats. Variance stats, because variance is the square of standard deviation, that's what we'll use when we're doing a standard deviation problem. Proportion stats is what we will use for this problem because we use that for proportion problems. But while I'm illustrating these, z-stats and t-stats, those will both be used when we're doing mean value problems, which is in 7.2, and we'll distinguish between those two when we're looking at section 2, next section. So proportion stats is the one I want for this problem. And we have 1 sample to work with. 2 samples, we'll begin to look at comparing 2 samples in chapter 9, but in chapters 7 and 8, we will use 1 sample under these stats choices. Now, in this case, they did give us the data, but the data is about something we're not looking at. We're not looking at the weights. So in this case, we're going to have to summarize the simple proportion of how many were red in the candies. So I'm going to go 1 sample with a summary. So those 4 stats choices, z-stats, t-stats, proportion stats, variance stats, we'll be using for the next few chapters. And because this is a proportion estimation, we're going to go to proportion stats, 1 sample with a summary. So all this tool wants is to know how many successes out of how many observations, because then you can create a proportion for your sample. And we're going to go to confidence interval because we are asked to produce a confidence interval. Notice already the default level for a confidence interval is 95%. You don't need to mess with the method here. It's automatically set to the default we want. So what are the number of successes? Well, we're supposed to be looking at how many candies were red, and it was 9 out of 34. So there were 9 that were red. That's considered a success out of 34 observations. So I literally put in how many were red, how many were observed, the confidence level I want, and it does it for me. And this is the kind of box we're going to be looking at quite regularly now for a while. So it tells us that this is a proportion calculation. The count was 9 out of 34. It tells us the sample proportion. So that would be the best point estimate. But then it has this standard error. So right away, standard error is not the margin of error. So you're going to ignore that if they ask for margin of error. In this case, they just want the interval. The interval is the lower and upper limits given here. So it says type an integer or decimal rounded to 1 decimal place. They've given us the proportion as a decimal, but they have a percent sign here. So they want the range of percent values rounded to 1 decimal. So that means I need to move the decimal place over 2 and then take 1 decimal place after that. So 0.116 becomes 11.6%. And 0.412 with a 9 following will be 41.2 rounded up to 41.3%. So by going to that tool, proportion stats, 1 sample with a summary, I put in the summary, 9 were red, 34 were looked at. I got this range of values here, and I entered those in, and I had to adjust decimal versions to percentages. All right, so let's just finish this up here. So then lastly, it just says, is the result consistent with 31% rate that is reported by the candy maker? Well, if we're 95% sure that the actual proportion of candies that they make is within this, that this range contains it, well, then 31% is realistic because the range contains that value. So yes, the confidence interval includes 31%, so that's consistent with the candy maker's claim. If it was not in that range, then I would say no. All right, so that's what it looks like to produce a proportion confidence interval. And here was an example problem done. I'll stop there and look in my StatCrunch videos to see other examples of other problems. Keep up the hard work.